Hi everyone, welcome back. You are watching the 12th lecture of EE635 Applied Linear Algebra. This happens to be the third and final module. Right. So far we have looked at this idea called the minimal polynomial of an operator, of a linear operator on a finite dimensional vector space. We have done some calculations pertaining to this minimal polynomial. I've given you some exercise problems, homework problems, which involves finding out the minimal polynomial of some matrices, right? And the promise is that with this minimal polynomial, we'll be able to do that, direct some decomposition of the whole space into smaller A invariant subspaces, right? But before we do that, we will have to familiarize ourselves a little more with this minimal polynomial and its properties, and a very nice property pertaining to polynomials. Yeah, we'll see that. So first, let me share my screen. Right, here we are. So, okay, so first we start with this, this question of how do you find out the minimal polynomial of a given linear operator, right? So we've seen that, okay, for some matrices we were able to find out its minimal polynomial. So let me refresh your memory as to memory about the definition of the minimal polynomial. The minimal polynomial is the least degree monic annihilating polynomial for a linear operator A. Yeah, so least degree monic annihilator polynomial. So that's the minimal polynomial. But from this definition, that is the least degree annihilator polynomial. From this definition, to find out the minimal polynomial for a given linear operator it's extremely difficult, if not impossible outright. So if somebody gives you an arbitrary matrix, like for example, suppose some matrix A equals, let us just take something 1, 2, 3, 4, 5, 6, 7, 8, 9. How do you find out its minimal polynomial? What is its minimal polynomial? How do I find out annihilating polynomials? First of all, how do I get the annihilating ideal of this matrix? And how do I find out the least degree annihilator? So it's a real mess. Is there a better way of doing it? Is there a more systematic way of doing it? By the way, there is some question that we overlooked in the last module. So we defined this annihilating ideal, right? Yeah, but remember this annihilating ideal, we said that this is generated by the minimal polynomial. But the thing is, in order to have a non-trivial generator, that is a non-zero generator, this annihilating ideal must be non-trivial, must be non-zero. Yeah, but what is the guarantee that this is going to be non-zero? Well, the guarantee comes from this fact that you see there is always a non-zero polynomial that is an annihilating polynomial. Why is that so? Well, see, A happens to be a linear operator from V to itself, right? Which then means A actually belongs to a vector space. That is the space of all linear operators. This is the space of all linear operators on V, right? Because V is finite dimensional, remember, dimension of V is n, which is less than infinite. Because this is finite dimensional, this space also is finite dimensional. And if you remember, this dimension is in fact equal to n squared. So because it's n squared dimension, I can have at most n squared linearly independent vectors, which means if I look at these operators, identity, then A squared, then A cubed, and so on up to A n squared, there are how many how many elements from LV? N squared plus 1. So this set cannot be linearly independent. This cannot be linearly independent in this vector space whose dimension is n squared, and this has n squared plus 1 number of vectors, which means there will be a non-trivial linear combination alpha 0 into identity plus alpha 1 into a plus alpha 2 into a squared plus dot 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 plus alpha n squared into a n squared that goes to 0, and this is a non-zero polynomial alpha 0 plus alpha 1 s plus dot 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 up to alpha n squared s to the n squared is a non-zero polynomial because this is a non-trivial linear combination, because LHS of star is a non-trivial. That means at least one of these coefficients alpha 0 up to alpha n squared are non-zero. LHS of star is non-trivial, is a non-trivial linear combination. Therefore, there exists. So let us call this polynomial, what should we call it? Let's say some fs. There exists this fs, which is in the annihilating ideal of A. Right? So that's the proof of the fact that this annihilating ideal is a non-trivial ideal. Okay, now coming back to the question of how to find out the minimal polynomial of a given operator. The path will be traced, the path to this method of the systematic method of finding out the minimal polynomial goes via one more definition, namely annihilating corresponding to a vector, right? So annihilating ideal with respect to a vector v, right? So what do we mean by that? So an suffix v a, this by definition is the collection of all polynomials fs. So suppose v is given, v in v is given, of course it's a non-zero vector given, defined as the collection of all polynomials such that, now notice carefully, fa, now I don't want fa to be identically, I don't want fa to be the zero operator. All I want is that fa annihilates v, that is fa kills v, right? Of course you can go ahead and check that this is an ideal. So homework to you, in fact it could be an immediate attention problem also, very easy to solve. Show that this is an ideal. Because it's an ideal, so by your homework, it's very simple to show this, show closed under addition and closed under multiplication from the ring. Because it's an ideal, polynomial ring is a PID, so there is a unique monic generator. So there exists a unique mu v in Fs, which is monic such that an VA is generated by mu v. So this mu v is the minimal polynomial of A with respect to a vector v. Minimal polynomial of A with respect to a vector v. Earlier it was those polynomials which kill every vector, because it's the zero operator, right? Zero operator kills every vector. Yeah. So earlier it was those polynomials which, when s is substituted by the operator a, gives me the zero operator. But here now I don't want zero operator. All I want is that given some non-zero vector v, I want that the polynomial operator kills just v. I collect them, that's an ideal, and because every ideal is a principal ideal, so there will be a unique monic generator, and here we have this this mu v. Once again, the question might arise that how do I know that this an v, so this annihilating ideal with respect to a vector v, how is this a non-trivial ideal? How do I know that? Well, once again, you can look at just this. You can look at v, a v, a squared v, dot up to a to the nv, right? How many vectors do I have? N plus 1. Can they be linearly independent? No, because all of them, because cannot be linearly independent, because n plus 1 number of vectors in V whose dimension is n. Yeah, n plus 1 is strictly bigger than n. So these vectors are not linearly independent. So they're linearly dependent, which means there exists alpha 0 dot up to alpha 0 dot up to alpha n in F, not all zeros, such that alpha 0 v plus alpha 1 a v plus dot up to alpha n a to the n v equals 0, which of course means alpha 0 identity plus dot up to alpha n a to the n v is equal to 0, which implies alpha 0 plus alpha 1 s plus dot up to alpha n s to the n is in an v. Yeah, that's it. So it's a non-trivial polynomial. So it's a non-zero polynomial which is there in this ideal, and therefore the ideal is also non-trivial. So there is a non-zero generator, yeah, mu v. Now, now here is the thing. Say v1, v2 dot vn. Say this is a basis, yeah. So let this be a basis for the vector space V. So this implies there will be a mu v1, there will be a mu v2, and so on up to mu vn. There will be n such polynomials, right? The thing is, the minimal polynomial of the operator A must then be the least common multiple of these minimal polynomials with respect to the vectors in the basis. Choose any basis, right? Yeah, and then look at these basis vectors and their corresponding minimal polynomials. Look at the least common multiple, you'll get the minimal polynomial of the whole operator. Now, why is that so? Okay. So let us recall the definition of LCM. This is something that you may have learned in your high school, perhaps 7th, 8th standard. There's the LCM of a few polynomials, right? So what do I mean by LCM? So suppose, so let's say I have some polynomials f1 up to f, say fn, yeah, like this. Then another polynomial f in fs monic is called the LCM of f1 up to fn if it satisfies the following two properties. Number one, that if I divides f for all I equal to 1 to n, that means all these polynomials will divide f, so f will be a multiple of all of them. So that's why it's the common multiple. Now, what is least about it? Least means if g is another polynomial, fs, such that if I divides g for all I equals 1 to n, then f must divide g. So among all those polynomials that are multiples of f1 up to fn, f happens to be the one which is kind of the smallest, because if there is any other multiple, then f is going to divide. It's going to be a multiple of f also. So that's least common multiple. All right. So the corresponding sort of dual idea of this is the greatest common divisor. So now let us define, now that we have defined this LCM, let us define that greatest common divisor also, GCD. So suppose f1 up to fn once again are polynomials in fs, then say gs monic. We insist on monic because of uniqueness. GS is said to be the, because of uniqueness I can call the GCD of f1 up to fn if it satisfies the following two properties. Number one, so compare this with the definition of LCM. Number one is that now G will divide Fi for all I equals 1 to n. So it's a divisor, it's going to divide Fi. And second one, that if H divides Fi for all I equals 1 to n, then H must divide G also. Yeah, so that's why it's the greatest common divisor. It's bigger than every other. So F1 up to Fn, all of them are multiples of G. If they're also multiples of something else, then the GCD will be multiple of that something else. So that's why GCD G is the greatest. Yeah, this greatest and least can be made sense of in terms of their degrees also. That's why. So that's the least degree for LCM, and GCD is the largest degree. So the largest degree common divisor, right? Of course, you have to insist on monic so that it becomes unique. Right. Now, so this fact that the minimal polynomial. So let us state this that as a lemma. So lemma mu must be the LCM of mu v1 up to mu vn. Yeah, is that all right? How do I prove this? So proof of two polynomials being equal often is done by saying that one divides the other, right? And because we are insisting on monicness, this is monic, this also is monic. So therefore, when one divides the other, it must be that same polynomial. Yeah, two monic polynomials will divide each other if and only if they are the same polynomials, right? So first, we are going to notice the fact that okay, so let us try and do the following. Let us try and show first that mu. So first, it would be worthwhile to define something. Let's define f to be equal to the LCM of mu v1 dot 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 up to mu vn, right? We want to prove that f is an annihilator. So first claim is that f belongs to annihilator of A. That means by definition fa must be 0, right? Well, why is that so? Well, f is the LCM, right? So f must be a multiple of mu v1, mu v2, and so on. So let I belong to the set 1 to n. Since f is the LCM of mu v1 dot 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 up to mu vn, there exists, say, qi polynomial such that if s is equal to qis into mu vis, yeah, which then means that fa now acting on vi must be equal to qi a mu Yeah, so you see f is a common multiple, so that's why we can write this, that it's a multiple of mu vi. So from this identity it follows that this into vi, but this goes to 0 because this guy kills it, right? This guy kills vi. There is an annihilating polynomial for vi with respect to vi, right? So this is 0, so this whole thing is 0. So this implies now let v in v be arbitrary, since v1 up to vn is a basis for v must be equal to some alpha 1, let me write, yeah, alpha 1 v1 plus dot 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 up to alpha n vn. This would mean f a v is equal to alpha 1 f a v1 plus dot 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 up to alpha n f a vn, but this star implies this is equal to 0, all of them is equal to 0, so this is equal to 0. Remember v was arbitrary, so fa kills every vector, so fa v equal to 0 for all v in v, which implies that fa must be the 0 operator. But if fa is a 0 operator, then that means f belongs to annihilator of a. Yeah, but if it is annihilator of a, then that means mu must divide f, right? So this is one direction. For the other direction, we have to show that f must divide mu, right? Now why is that so? Now in order to show that, what we'll do is we'll use the definition of LCM, and we'll use a very nice property that this mu vi's have in relation to this mu's. Yeah, now what is that? Okay, so we have to pay some attention. Yeah, so this may seem like a digress, but it's not. Let's see what relation does mu vi's have with mu, right? So I say that each of these mu vi must divide mu. So here is the claim. Claim is that mu vi must divide mu for all I from 1 to n, right? Now why is that so? Okay, once again the trick would be the following. Trick would be proof by contradiction. Suppose it doesn't, suppose not, then what does that mean? We know from polynomial algebra that this means if it doesn't divide, then this means mu s can be written as some q I s mu v I s plus an r I s, where this degree of Ri is strictly less than degree of mu Vi, right? This is just long division, and because I'm saying that this doesn't divide, so there is this non-zero remainder. But then this will lead to a contradiction. How? See, same trick, we have used this trick before also. So only this small trick, small, very trivial tricks from high school algebra can take us so far, right? So now see how does this give us the contradiction? Well, you see, mu is minimal polynomial, so mu a must be 0, so mu a v must also be 0, right? So I can write okay, let me get rid of this part, right? So I'm writing it as 0 is equal to mu a v, that must be equal to q I a some polynomial mu v I a acting on v plus r I a acting on v, right? Which v? Not any old v, but let's say vi, yeah, vi. But mu vi a vi, this is the annihilator polynomial with respect to Vi. So when it acts upon Vi, it must produce 0. This goes to 0, which then means that this is equal to Ri a Vi. Yeah, that is equal to 0. Left hand side was 0. Now therein lies the contradiction. Mu Vi happens to be the least degree monic polynomial that kills Vi. But now here is a lesser degree polynomial that kills Vi. That's a contradiction. So what is the only option left to us? This has to be 0. So this implies RIS must be 0, which means that which means mu Vi must divide mu, right? For all I equals 1 to n, right? So if that is the situation, then this means LCM of mu V1 up to mu Vn, which is f, that must also divide mu. Yeah, that is the property of an LCM, right? That, where is it? LCM definition. Yeah. So if G is such that Fi divides the G, then F must also divide G, which is the LCM of Fi's. So here mu Vi's divide mu, and therefore LCM of mu Vi's, which is F, must also divide mu. That's what we have written. Yeah, which divides what? This may become confusing, but if you just think straight, it will be absolutely simple. There's nothing in it. So what is the outcome of this lemma? The outcome of this lemma is that if I can somehow fix a basis and find out these minimal polynomials with respect to the basis vectors, which can be done by the following method, then I just take the LCM of that and I'm done. LCM of these polynomials, that will be minimal polynomial, the minimal polynomial for the whole operator, for the whole vector space. Yeah. So how do I get mu V1? So for that matter, let's say, how do I get mu V? So how to get this minimal polynomial of a vector? Well, all I have to do is all I have to do is the following. So like, for example, once again, let us look at this matrix A. Yeah, let's try and understand this with the help of a matrix. 1 2 3 4 5 6 7 8 9. And what I do is I want to find out mu E1, right? So what is E1? E1 is my first basis vector 1 0 0. Okay, so I look at E1, then I look at AE1, which is AE1, and see whether they're dependent or not. If they're not dependent, then there's a linear combination which goes to 0. That gives me a degree 1 polynomial which kills E1. And I know that there is no lesser degree polynomial which will kill E1, because less than degree 1 is degree 0, which is any constant, and no constant can kill E1, right? Because E1 is a non-zero vector. So then I know that there is this least degree polynomial, degree 1, which kills this, and that must be the minimal polynomial. Make it monic, that must be the minimal polynomial of A with respect to E1. What is this in this particular case? Well, in this particular case, AE1 is equal to 147. So what are these two vectors? Now I have 1 0 0 and I have 1 4 7. Of course, they are not dependent. They are linearly independent. These two are not linear combinations. So I mean, their linear combinations cannot go to 0. Non-trivial linear combinations cannot go to 0. Right? So I have these two vectors whose linear combination doesn't go to 0. So the minimal polynomial of E1 cannot be degree 1. So I have to move to a higher degree. So degree 2. So what should I do? I look at once again E1. I have A E1. Now I look at A squared E1. Yeah. What is that? I have 1 0 0. I have 1 4 7. Now what will I have? I have 1 4 7 multiplying this. So let me do this calculation. I have 1, 4, 7, 2, 3, 5, 6, 8, 9. This multiplying 1, 4, 7 is a squared e1, which happens to be 1 times 1, 4, 7 plus 4 times 2, 5, 8 plus 7 times 3, 6, 9. What is that? That happens to be 147 plus 8, 20, 32 plus 21, 42, 63. What is this? This is 30. This is 66. Yeah, this is 65, 95, 102. This is the third vector. So what here it should be this and 30, 66, 102. 30, 66, 102. In most likelihood, they are also linearly independent, right? And then I will have the final one. I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. This matrix multiplying 30, 66, 102. What will it give me? This is a cube e1. That will be some vector. I'm not calculating it. Let me call it b1, b2, b3. And then all I have to do is I have to look at e1, a e1, a squared e1. This is a matrix 3 by 3. I need to find out alpha 0, alpha 1, alpha 2, so that this is equal to this b1, b2, b3, which is my a cube e1. When I find alpha 0, alpha 1, alpha 2, then that means a cube e1 minus alpha 2 a squared e1 minus alpha 1 a e1 minus alpha 0 e1 must be 0, which would then mean s cube minus alpha 2 s squared minus alpha 1 s minus alpha naught into 1. This is a polynomial that, so this is the monic polynomial of least degree, which is equal to mu e1 s, right? So by this technique, I have to repeat this technique for e1, e2, e3. Then those polynomials, I just have to find out their LCM. That will be mu for the whole thing. So try this exercise for various different matrices. I mean, one homework could be just complete this exercise. Right? So that's how we get the the minimal polynomial of the whole with respect to all the vectors. That means the minimal polynomial of the operator. Right? I hope you understand what's going on. So we have looked at these two distinct concepts, namely one is the minimal polynomial of the whole operator, and then minimal polynomial with respect to vectors, with respect to given non-zero vectors. But the interesting fact is that if those given non-zero vectors happen to be basis vectors, then those minimal polynomials are special, right? And those minimal polynomials, if you look at their LCM, then that LCM is the minimal polynomial of the whole operator. But this exercise has also shown us something very interesting, that minimal polynomials with respect to these vectors, they must all be factors of this minimal polynomial of the operator. Indeed, you see, so let me just write this down and you prove this as a homework. This is something that we have already done, in one of the, as a part of the proof, but just try and do it yourself now with whatever you understand about these minimal polynomials. So let's say let v in v be arbitrary non-zero vector, yeah, then mu v must divide mu. So if you look at this mu, somehow suppose we know this mu, then for these different vectors, all the vectors that we have there in the vector space, if I try and find out their minimal polynomials, I mean minimal polynomials with respect to those vectors, then I have only finitely many choices. I mean, finitely many possibilities. Yeah. Why? Because this mu v must actually be a factor of mu. And how many factors are there? Only finitely many factors of mu are there. Right. So let us try and see this from the perspective of a, let's put this to perspective, like suppose mu s polynomial happens to be, say, s minus 1 the whole squared into s plus 2 into s minus 3. Then for a given vector, what could be its minimal polynomial? It could either be s minus 1 or s minus 1 whole square or s plus 2 or s minus 3 or s minus 1 into s minus 2, sorry, s plus 2, and so on, all possible factors. Among all possible factors, one of them would be the minimal polynomial of this given vector. Yeah. So now in this situation, right, what can we say about these factors, right? And as we'll see that these factors of the minimal polynomial are the ones, which are going to finally give us those A invariant subspaces, which can be used to write the whole space as a direct sum decomposition of these A invariant subspaces. So what can we say about these factors? The first thing that we're going to notice about these factors is that these factors have something to do with the eigenvalues, right? So say, now what are the eigenvalues? Eigenvalues are roots of the characteristic polynomial. So here is the fact that we are going to prove now. The minimal polynomial, the roots of the minimal polynomial and the roots of the characteristic polynomial are exactly the same. The two sets are exactly the same. Yeah, so let me repeat that the roots of the characteristic polynomial, that is the eigenvalues, and roots of the minimal polynomial are precisely the same. That means the roots of the minimal polynomial are also the eigenvalues, or rather eigenvalues can also be defined as roots of the minimal polynomial instead of the characteristic polynomial. And remember, those are the factors. So roots means you can factorize the whole polynomial. So if the polynomial does not factorize in the field, but it factorizes in a bigger field, then we go to that bigger field, and in that bigger field we have to write this polynomial into these as a product of these linear factors. Each linear factor in the product correspond to an eigenvalue. So what we are saying here is that the minimal polynomial and characteristic polynomial have exactly the same set of roots, namely the eigenvalues. Only thing that differs is their multiplicities. And as we'll see, but not in this lecture, but in a future lecture, that is either 13th or 14th lecture, we'll see that the minimal polynomial will also divide the characteristic polynomial, which means characteristic polynomial is also an annihilator. This is the celebrated Cayley-Hamilton theorem, that characteristic polynomial is an annihilating polynomial. That means in the characteristic polynomial, replace S by A, you get the zero matrix. Quite surprising, right? Because you have formed characteristic polynomial by looking at this Si minus A and its determinant. It's some weird way of looking at it, but it turns out that you replace S by A, you get zero. Anyways, so let us try and prove this particular fact about the factors, and then we'll stop. Then we'll stop after seeing one particular result, which will sort of set the tune for the next lecture, where we actually see this direct sum decomposition of the whole space in its full glory. Okay, so but before that we prove this property with the roots. Okay, so here is the thing. Should we call it a lemma or a theorem? Let's say theorem. Makes us feel good, no, that we are proving a theorem. So all definitions in place. I'm not writing all of them. Roots of mu is equal to roots of chi. Yeah, so the roots of the characteristic polynomial and roots of the minimal polynomial are exactly the same. Okay, so how do we prove this? So once again, when we have to prove something, uh, we have to prove equality of two sets. We have to show containment of one set in the other, right? How do we do that? Okay, so so let us see which direction should we prove first. Should we prove the easy direction first? So let's prove the easy direction first. So we would like to prove that roots of mu contain roots of chi, right? So let's say now here, for the benefit of our calculations, we are going to assume that everything is happening over. So F is algebraically closed. What does that mean? Is that every polynomial factorizes into linear factors. Closed. That is, every polynomial factorizes into linear factors. For example, F could be equal to complex numbers. So over complex numbers, we know that every polynomial factorizes into linear factors. If not, then you have to, if it's a real polynomial, so suppose F is R, then we just have to let things happen over C. Yeah, so that's the bit small technicality, but I think you can make peace with that. Okay. Now, so we want to prove that roots of chi is contained in roots of mu. So suppose lambda belongs to the roots of chi, right? Which means determinant lambda I minus a is equal to 0. But this means there exists v not equal to 0 such that lambda I minus a into v is equal to 0, right? But this means what? This means s minus lambda is annihilator, annihilator with respect to this non-zero vector v, right? And of course v is non-zero, so no smaller degree polynomial kills it. This is monic also, which means mu v s must be equal to s minus lambda, since no smaller degree polynomial can annihilate v. Yeah, so this is mu v, but we have already proved that mu v must divide mu, which then means s minus lambda divides mu, which means mu can be written as sum qs into s minus lambda, which means lambda is a root of mu. And that's what we wanted to prove. So one direction is done. Now the other direction, what we would like to prove, where did we write? Yes, this is what we proved. What we would like to prove now is the other way around. Roots mu is contained in roots chi, which means we have to prove that the roots of mu are are in fact eigenvalues, right? How do we do that? Well, so let lambda be a root of mu, yeah, root of the minimal polynomial. This means mu s can be written as sum qs into S minus lambda, right? Must be a factor of mu, right? Now, this implies mu A V is equal to QA A minus lambda I V. This must be 0 because mu A is 0, right? But now here is the thing. There exists a V such that QAV is not equal to 0, right? This requires some thinking. This requires some argument. What am I saying? I'm saying that there exists some V such that QAV is not equal to 0. Suppose not, what would have happened? So listen carefully. If QAV were 0 for all V, then that means QA would have been 0, the 0 operator. But if QA is the 0 operator, then it's an annihilator. But what is the degree of Q? The degree of Q is strictly less than degree of mu because Q is a factor and there is a non-trivial factor S minus lambda sitting there. Degree of Q certainly is strictly less than degree of mu, isn't it? Right? So if degree is less and it's an annihilator, that's a contradiction because mu is the least degree polynomial. Yeah. So therefore, QAV cannot be 0 for all V. Therefore, there exists a V such that QAV is non-zero. Yeah. So define this non-zero vector. So define W as QAV, which is not equal to 0. So then this would mean mu AV, which is equal to A, okay, which is equal to QA A minus lambda IV, but that's the same as I've said before, that they commute because they are all polynomials in A. QAV equal to 0, right? This is the same as A minus lambda I into W equal to 0. But that means AW is equal to lambda W with W not equal to 0. So here I have a non-zero vector which satisfies this equation. So this must be an eigenvector, which means lambda must be an eigenvalue. That's it. This is the other direction. So we have proved it. Right? So you see, minimal polynomials, roots of them are precisely the eigenvalues, nothing more, nothing less. Only their degrees differ. Only their degrees differ. So as a corollary to this particular fact, so suppose the characteristic polynomial was indeed a product of all linear factors, distinct roots. So n distinct roots. In that case, there is no choice but for the minimal polynomial also to be equal to the characteristic polynomial. Right? Okay, now with this, we are almost at the end of this module. What we will do is we'll get back to this idea of GCD. So we have seen something about the LCM. We'll get back to the idea of GCD. So first thing that I want you guys to prove is the fact that okay. So you remember this ideal generated by some polynomials, right? F1 up to Fn. Prove that this is the same as the ideal generated by GCD of F1 up to Fn. Just do this, yeah. What will set up the tone for the next lecture is that, so there we're going to do this full decomposition of a vector space into A invariant subspaces, direct sum decomposition. That will be done by this ancient theorem called Aryabhatta Bezu identity, which has something to do with the GCD. So here is this thing, we call it AB, or Aryabhatta Bezu identity. What is this identity? What is this identity? It says that, say, f and g are, okay, say f1 and f2 are two polynomials, right? And suppose g is the GCD of f1 and f2, then there exists polynomials a1s and a2s such that I'm going to get rid of the arguments. G, the GCD, is equal to a1 f1 plus a2 f2. This is Aryabhatta-Bezu identity. Aryabhatta actually proved this for integers, positive integers, and not positive, in positive, negative, both kind of integers. So he proved it for integers, but it actually is true for any for polynomial rings also, right? This is something that we're going to use crucially, right? So just brush up your memory about co-prime polynomials. So what do we mean by co-prime or relatively prime polynomials? Relatively prime polynomials mean that, so f1 and f2 would be called relatively prime or co-prime if their GCD is 1. Yeah, that is that, the monic greatest common divisor is just 1. That means they don't have any common factors. Okay, so that means in that scenario we'll be able to find polynomials in a1 and a2 such that 1 is equal to a1 f1 plus a2 f2, and we'll see that this particular identity would enable us with such a strong tool, with the help of which we'll be able to decompose the whole space into these smaller A invariant subspaces. Yeah, so just brush up your memory and try to find out a sort of argument which supports this Bezu identity, Aryabhatta-Bezu identity. All right, so I urge you to go through these video lectures like before, like always. Yeah, please go through these video lectures and solve these homework problems, and please get back to me if you face any difficulty. Okay, so most likely we'll have only 2 more lectures, 13 and 14, and there we will see in lecture number 13 we'll use this Bezu identity to finally do the decomposition, and we'll see how further we can move with that decomposition. The ultimate result that will come out of this exercise will be the idea of a Jordan canonical form. Okay, so till then, take care. Bye bye.